Varistors, let's talk about them. It comes from the combination of two words, which is resistor, which is basically this. We all know what resistors look like, and voltage. So the resistance of the component will depend on how much voltage we are passing through it. And it will be rated between a minimum and a maximum voltage to know how much to let pass and for your application. In this case, this is a metal oxide varistor, just the material that's inside it. And this one has a model number of 271KD07. And according, this is just a general data sheet, but the numbers for this one would let a minimum voltage of around 175 volts to 220 volts. 225 volts go through. So that's the minimum and the maximum. In practice, it might be different because nothing is perfect. Second is they have plenty of applications, which are surge protection in consumer or industrial electronics, surge protection in home appliances. So basically, you would have the city power, which is generating a sine volt, a sine signal, should be like this, and it has an RMS of about 225 volts. If there was lightning or a surge or spike in voltage or current, we would have an anomaly that would look like this. Or we might have some type of fuzziness along the way. To protect the equipment and the appliances from a spike like this, we would use a varistor that's included in a surge protector. So it will suppress this spike and the equipment doesn't experience a sudden impulse of voltage or current. Normally, with it, they would put a choke so that it can smooth out the signal and the equipment can experience a smooth signal. So let's talk about what kind of circuit we can use with this varistor, and let's go over the datasheet real quick. In general, wide operating voltage, zoom in a bit more. We have a wide operating voltage, range from 18 to 820 volts. It depends on the part number. Fast responding to transient over voltage, which is what we spoke over here. Large absorbing transient energy capability. Low clamping ratio and no follow-on current. And those are just some technical specifications. It can operate in really cold or really hot, and we can store it in really cold or really hot. And the applications, like we said, we can have it in transistor, diode, IC, thyristor, and triac semiconductor protection, surge protection, just like we spoke, and relay and electromagnetic valve surge absorption. And apparently, for this part number 27, we have 271 varistor voltage. So we have 271 in our case. So that's 180. I'm trying to understand what they mean here. If it's 180, 18 volts, 101, 100 volts. Oh, so this would be maybe because there's a 0, 18 volts. Not sure. Not sure how to interpret that. We have the tolerance. What is the tolerance that we have here? K, 10% tolerance. And D is the type of, it's a disk. Element diameter, so just the measurement. And the type of packing, which is written in, that's so small. 0TR, 07, I guess. The part number on here is a little bit different than the composition of this, but most of it is the same. Anyway, let us try to see what kind of a circuit we can do. So, if I have, let's do something simple, no fancy stuff. Let's start with a block diagram. We can have a block over here that's for the surge protection. Let's get another pen that's a bit thinner. That's for the surge protection plus stepping down of the voltage. Okay. Or not surge, surge protection over voltage protection. That's the first block diagram. Then it will go into a rectification stage. And lastly, we can have it go through a filtering stage, which is normally, if you want to convert from AC to DC, would be a low pass filter, which would be capacitors and all that stuff. It can be as sophisticated as you want, or it can be very simple. We're going to go with very simple to see how it behaves. So we will probably go with a capacitor to ground, a shunt capacitor. Many people, you can also do, if you want to make it more sophisticated, you can have a pi bridge. You can have an inductor with a capacitor like that. That also works. And at the end, we're going to have the voltage regulation stage, which we can use a Zener diode. We can have a Zener diode for however much volt we want, 12 volt, 6 volt, 8 volt, 5 volt, 3.3 volt. We can have a Zener diode in place, and then we can have the output. As for the rectification stage, which is obvious, we will have a full bridge rectifier. Okay. And the stepping down, which would be the Varistor that we just explained, which I assume the sign is like this. Let's make that look nicer. The Varistor over there. And then we can have a series capacitor and some sort of a resistance that would go on to the full bridge rectifier, and then it will go on to the filtering stage, and then it will go on to the voltage regulation stage. Yeah, that should work. Of course, this is something that's very basic. You can have it even more sophisticated by adding maybe a pre-filtering stage over here with another capacitor, shunt capacitor, before it goes here. But normally, we'll just put the filtering stage after the full bridge rectifier. And we should get a clean signal after that. If you realized something, we didn't put a certain component, because we don't need it. We were able to not include a transformer, a step-down transformer. Instead of going 220 volt directly to voltage regulation, to step-down voltage, 220 to, for example, 12 volts, through a transformer, we did it this way. And the advantages over here, apart from like having a switch mode power supply, for example, is we can make it smaller. It can become more compact in one way or another, depending on the values that you choose, the application, and the components that you have on hand. So let's put the circuit together and put it to work. The very first step that we are going to do is take the varistor and take it from the positive and plug it into the breadboard. Let's see. I know that the wall voltage over here, over there, is going to be 220 volts. If I take this and just stick my probes in there properly, I am going to have, where's my multimeter? I'm going to have around through 230 volts approximately. That's the wall outlet. Okay, let's see when I put it in series with the varistor how the voltage will drop. This is my positive and this is my negative. It stepped down a lot through the varistor. From 230 volts, we now have about 105 volts AC, which is actually pretty good for a step down voltage. So we've almost cut it down by half. Okay, let's unplug. Now, let's get a shunt capacitor. This is going to be, let me just fix the camera angle a bit. This is going to be a 2.2 microfarad capacitor, electrolytic capacitor at 400 volts, which is safe, which is good. So I'm going to put this in series with the varistor, just like that. And let's see how much voltage we get now. So positive side on the end of the capacitor and the negative on the negative. Okay, still the same amount of the same amount of voltage because it's AC, and when you have an AC voltage, there's a frequency, so the resistance of the capacitor will decrease. Even if let's see the frequency that we have. Uh, 50 hertz. So definitely the capacitor is going to be like a short circuit because we have frequency. Okay, unplug. Now I'm going to take a resistor. What is the value of this resistor? Maybe we can also take a look at the waveforms on the oscilloscope so that we can understand what's going on. This resistor is 1.4K. Just good. That over there. Let's first see the voltage. So on the output of the capacitor only, we said we have 105 volts, 105 volts AC. After the resistor, 104 volts, 105 volts. So not that much big of a difference. However, I want to take a look at it under the oscilloscope. I'm sure there's going to be some charging and discharging. Yeah, so there's some charging and discharging right there. If we take 10 volts per division, 10, 20, 30, 40, and of course it's going up and up, but I think this is the maximum my oscilloscope will go to. The stepping down of the circuit has happened. We stepped it down by a fair much. From 225 volts to 100 volts, which is pretty good. So this stage is complete. We put the varistor, capacitor, resistor. Now we can take a full bridge rectifier and we can use this one. It has the built-in diodes and everything. So this makes things a lot easier. We know where to put the AC signal in, and we know where to take out the rectified signal. So let's put this one. What we've done is I put the bridge rectifier and I got an output from the positive and the negative. Let's see the voltage drop. Let's see, so I have the positive over here, negative over here. I have now 40 volts AC. Do I have any DC component? 94 volts DC. So it's like it balanced out. It's like it took some of the AC, which is what it did, and rectified it, but there is still some AC component left. And that AC component that's left is going to look something like that. So that's our, if we change the coupling, so that's the AC component, and that's the DC component. Okay, very good. So what have we done so far? We've taken care of the rectification. The last part is to do the filtering. The filtering for all that waveform so that it's nice and stable. We can use another capacitor in shunt with it. Okay, I have positive over here and I have negative over here. 55 volts DC, really good. And AC, 0 volts AC. So we have completely filtered out the signal at this point. Lovely. That's excellent. And let's see our signal. My oscilloscope is running on low battery. It's over the limit. Because if we want to take the divisions, let's try to lower the starting position. There we go. That's our DC signal. I lowered it from the 0 offset. So that's our signal now. Maybe if we can try and zoom onto it, time base. Yeah, it actually looks good. It's really good. It's perfect. Okay. So at this point, I don't think there is a need to filter further because we got the results that we want. So we finished this part. We just put a shunt capacitor. Now we need to put the voltage regulator, and I have this Zener diode. You can use the Zener diode across the capacitor. So we'll just take that. Let's move the capacitor over. Just like that. And now let's take a look at the voltage output. I have 11 volts DC, 12 volts, say. And our oscilloscope signal is absolutely lovely because we can higher this so that it's back. Let us do an auto calibration, makes things easier. There we go. That's our signal. 5, 10, 11, 12. That's our DC signal. And to see that it actually works, not just we're seeing them on graphs, we can have a nice little LED and resistor. I have an LED coming out of the Zener diode in parallel. and connect a 330 ohm resistor. I don't know if you saw how it blinked very quickly. It was discharging the capacitor. And now we can turn it on. It's doing just fine. There we go. That's a step down voltage. It might be blinking quickly because of the frame rate of the camera, but from my side, it's not blinking at all. It's doing just fine. And let's see the oscilloscope waveform to see how the signal is behaving. Hmm. Where would we want to put this one? Like right here. And see, the reason why it's blinking is because the capacitor charge and discharge. That's the capacitor charging and discharging in the AC domain. The way we can sort this out is by getting a different value capacitor. I think this capacitor is a bit too big at 2.2 microfarad, so we would want to consider something at 1 microfarad perhaps. We would get better results, but I don't have any 1 microfarad capacitors. This is the only one. Or I may have 1 microfarad capacitors, but they would be at a too low voltage for this application. So that's it. We were able to step down 220 volts AC into regulated 12 volt depending on your Zener voltage and turn on an LED. This is very advantageous when you want to minimize your power supply, and it's a good application for Varistor. And we followed exactly our block diagram over here and the circuit for everything.